Hi everyone, this lesson is concerned with statistical estimation. The problem here is as follows. We're given a sample of draws from a certain distribution and we would like to know what the data tells us about the distribution. In other words, what can we infer about the distribution? We've already looked at some non-parametric ways of doing this, for example via the histogram or the empirical distribution function. Here we will be mostly concerned with point estimation. For example, we might be given a dataset which contains the number of bond defaults per quarter. We might assume that the data comes from a Poisson distribution and we need to estimate the rate parameter lambda. What is the best way of doing this? We will also be interested in obtaining confidence intervals for that parameter. We'll do this in a variety of ways. In particular, we will look at the bootstrap, which is a non-parametric way of determining confidence intervals. We will also introduce the method of moments and maximum likelihood estimation as a means of determining these parameters. So let's begin. A good source for this material is the book by Wasserman called All of Statistics, chapters 6 to 9. As I mentioned, the problem is the following. We're given a data set x1, x2 up to xn from a common distribution f, and we'd like to infer some properties of the distribution f. Now, a statistical model is simply a set of distributions or densities, and such a model can be parametric or non-parametric. In the parametric case, we're given a finite number of parameters which parameterizes the distributions in f, in other words, which characterize them. Non-parametric just means not parametric. Some non-parametric estimation that we've already done is obtaining the empirical CDF, histograms, and kernel density estimates. A parametric model typically takes the following form. It's a collection f of density functions, say, characterized by some parameters theta. Each of these thetas is a vector of parameters which may belong to a certain set. In other words, f is a density function and theta here is a vector of possible parameters taken from some subset of r to the m. For example, if we assume that the data are normally distributed, then f is the collection of all normal density functions, which is characterized by two parameters, mu and sigma, where mu, the mean, can be any real number whatsoever, and sigma must be a real number which is strictly greater than 0. So we have here a two-parameter model where the vector theta consists of the two parameters mu and sigma. In other words, theta 1 is equal to mu, and theta 2 is equal to sigma. Another example, here the collection f is the set of all exponential density functions. That's a one-parameter model that assumes that the data is exponentially distributed with rate parameter lambda. And here lambda has to be greater or equal to 0. Suppose now that we're given a sample x1, x2 up to xn of independent identically distributed draws from some distribution f, and we might want to obtain an estimate of a quantity theta. That theta might be a statistic, such as the mean, the variance or kurtosis associated with f, or we may have reason to believe that the xi are independent draws from a distribution with a density function fx theta, which is characterized by the parameters theta, and we'd like to estimate those parameters. Or theta may even be the CDF or PDF. Now a point estimate of theta, denoted by theta hat n, where the hat indicates that it's an estimate and the n indicates the sample size, is a single best estimate of the quantity theta. Now given a sample x1 up to xn, the point estimate theta hat n of theta depends on the data, and the data are random, and hence theta hat n is random as well. In other words, theta hat n is a random variable. As it is a random variable, it has a distribution, and that distribution is called the sampling distribution. In particular, it has a mean and a standard deviation. The distance from the mean of the estimator and the true value of the parameter is called the bias. The standard deviation of the estimator is called the standard error. A point estimator theta hat n of a parameter theta is called unbiased if its bias is 0, in other words, if the expectation of the estimator is equal to the true value. By the way, this subscript over here means that we're taking a probability or an expectation, assuming that the density has a parameter whose true value is theta. An estimator is said to be consistent if theta hat n approaches theta as n goes to infinity, in other words, as the sample size increases. This can be the case even for biased estimators, as we'll see in a minute. And a point estimator is called efficient if its standard error is small, in other words, if the standard deviation of the estimator considered as a random variable is small, which means it's concentrated near a point. As an example, we saw earlier in the lecture on probability theory and statistics that the estimator of the variance given by the sum of the squares of the differences shown here has a mean which is not equal to the true variance sigma squared, but slightly less than it because of this factor n minus 1 over n. So it's negatively biased. Nevertheless, as n goes to infinity, n minus 1 over n goes to 1, and so the estimator does in fact converge to sigma squared. In other words, the estimator is efficient. We also saw that this different estimator, which has a 1 over n minus 1 over here rather than a 1 over n as shown here, is unbiased, which is why it is used in statistics. The quality of a point estimate can be assessed by the so-called mean squared error, which is defined to be the expectation of the distance between the estimator and the true value squared. This can be decomposed into a sum of two squares, namely the mean squared error is equal to the bias squared plus the standard error squared. So a good estimator will have both a small bias and a small standard error. To see that this equation holds, let us define theta bar n to be the mean of the estimator. In other words, the bias is just theta bar n minus theta. And then if we look at the expectation of the difference squared, we can add and subtract a term in the middle, which does nothing. And then consider this as a plus b all squared, which of course is a squared plus 2ab plus b squared. This is the a squared term, the 2ab term, and the b squared term. And then we observe that the expectation of this random variable over here is just this. So the middle term is 0. The first term is just the standard error squared, and the last term by definition is the bias squared. Now, one important fact that we will use later but won't actually prove is the following. Many estimators are asymptotically normal. In other words, if we look at this ratio over here consisting of the random variable, which is the estimator, minus its true value divided by its standard error or standard deviation, then the distribution of this looks more and more like a standard normal distribution as n goes to infinity. Let's look at an example. Suppose that we have x1, x2 up to xn, and that these are draws from a distribution f with an unknown mean mu and an unknown variance sigma squared. And suppose that we want to estimate mu. We already know that the sample mean, denoted here by mu hat n, which is just x bar n, and is defined to be the average of the values of the sample points, is an unbiased estimate of mu. Furthermore, the central limit theorem states that for large n, x bar n is approximately normally distributive with mean mu and variance sigma squared over n. In other words, x bar n minus mu divided by sigma over the square root of n is approximately standard normal. All we've done over here is we've subtracted the mean of the random variable x bar n and divided it through by its standard deviation, in other words, the square root of its variance. If we take different draws from f, we will get different estimates of mu. In other words, a different sample will give us a different estimate. Remember that the estimator is a random variable. So by repeating the experiment of drawing n variates from f, we will get an estimate of the distribution of the random variable mu hat n. Let's make this more concrete. Suppose that n is equal to 20 and capital N is equal to 1000. Okay? Let's make this example a little bit more concrete. Suppose we would like to estimate the distribution of the random variable mu hat little n, where little n is equal to 20. What we're going to do is we're going to draw a number capital N is equal to 1000 draws from the distribution of mu hat n. So we're going to generate a little n by capital N matrix X of random numbers drawn from the Poisson 2 distribution. In other words, the rate parameter lambda here is equal to 2. This matrix has little n many rows and capital N many columns. You can regard every column vector as a sample of 20 draws from the Poisson distribution. If you take the mean of every column, you are going to get 1000 many estimates of the mean. In other words, we're going to get 1000 draws from the sampling distribution of mu hat 20. Then, if you plot a histogram and a QQ plot of this vector of the means estimates, you will see that mu hat n is approximately normally distributed. So let's have a look at this example again. We set the rate parameter lambda is equal to 2, little n equal to 20, capital N equal to 1000, and we have a matrix X, which is a little n by capital N matrix of draws from the Poisson distribution with parameter lambda equals 2. So that's a 20 by 1000 matrix, and these are the draws from the Poisson distribution. As you can see, these are all integers as they should be. Now we take the mean of each of these columns, and that will give us a vector of 1000 sample means, where each mean is from a sample of size 20. If I now plot a histogram and a QQ plot, the histogram looks quite normal. The red curve is the corresponding normal density curve. Remember that the Poisson lambda distribution has a mean of lambda and a variance of lambda also. In particular, in this case, the mean is 2, and because we're taking the mean of a sum of n many random variables, we have to divide through by the square root of n in order to get the standard deviation. The QQ plot is also along the line y is equal to x. In other words, what we can deduce here is that hat mu n is approximately normally distributed with mean 2 and variance equal to 2 over n.